5 or 5.3 today. We're going to skip 5.2 for now. We'll circle back to that in another lesson or two. So nobody gets scared here. Ah! I used the P word in math class, which is everybody's, should have done this on Halloween, on hindsight. That would have been the scariest yet. Proving identities. I know that everyone gets freaked out when they see the P word in mathematics class. I know geometry might not have been kind to you in that regard. Here's the deal. With what I'm going to be asking you to do today, this is no different than we did last class. And in a way, it's actually going to be easier because you have the answer that you're looking for at the start. Okay? So the goal is going to be like, you have a start, you have a finish. Your job is going to be to fill in the steps in between. That's going to be the problem, is filling in the steps in between. But it's ostensibly the same thing we did last class. But now you know where the finish line is. Instead of before where it's like, am I done? Am I not done? Is there more to do? I'm not sure. Here you know. Okay? So I want to point out a few helpful strategies that we can use. And these strategies could also really be used in the simplifying problems we've done before. So for these identities, you must start on one side of the problem and finish on the other. You can't do anything to both sides. That's perfect, thank you. You can't do something to both sides of the equation. You have to start on one and finish at the other. You can't cross multiply. You can't clear fractions. You're not allowed to do stuff like that. Okay? Typically, you want to begin with the more complicated side. We'll talk about what complicated means in the context of these problems. But typically in a proof, it's going to be easier to start with the more complicated side and cancel stuff out, then build up from the less complicated side into something that's complicated. In general, that's start with the more complicated side. If you get stuck, changing everything into sines and cosines is usually an effective strategy to get you to the finish line. May not be the shortest, but it usually is will help you kind of see your way through. If you're like, I don't have any idea how I'm going to get from here to here. If I kind of convert everything into sines and cosines, usually we can kind of stumble our way to the finish line after that. Remember to combine fractions, you need a common denominator. The difference of two squares factoring pattern is often really helpful, that a squared minus b squared is equal to a plus b times a minus b. In particular, that's a way to kind of generate a Pythagorean identity. Like if I have 1 plus sine in a fraction, if I multiply the top and bottom by 1 minus sine, 1 plus sine times 1 minus sine is 1 minus sine squared. That's the difference of two squares, which I would recognize as cosine squared, right? That was one of our versions of P1. And then lastly is always kind of keep an eye on where you're trying to get to. That'll often help you eliminate possible choices. If you're like, oh, I need this denominator to look like this, it tells you oh, well, let's multiply the top and bottom of this fraction by something so I can get the denominator I need in the final product. There may not be a good reason to do it other than where you're trying to get to. So always kind of keeping an eye on where you're heading really can help us make some choices. Now, It's really 3, 4, and 5 that are going to be the ones that you could also use in the simplifying problems we've done before. Those are often helpful, even in that context. And the plan here is I'm going to work through a couple of examples myself. And then I gave you guys a note sheet that will kind of call on some random people to help us kind of work our way through, talk about strategy and how to kind of get things started, and all that jazz. But first, we're going to have Mr. Kulik do some examples here as soon as this stupid thing gets out of my way. All right. So here we're asked to prove the identity. We have tan x plus cotangent x equals secant x plus cosecant x. While I'm working on this, I would encourage you to have your identity sheet out so that you can kind of follow along on one of those. Again, super duper helpful to have so that you can be looking at the same thing I am. If you are missing your identity sheet, oh no, keep a better handle on this thing, but I have extras on top of the file cabinet if you need one. But everybody's gotten one, I think, and maybe more than one for some of us. Oh man. But it's okay. If you need another one, go grab one. All right. So the first thing I want to do is identify which is the more complicated side. Now, in terms of these types of problems, if I look at the left-hand side, I see two terms because I have two things being added together, right? On the right-hand side, I see one term. The two things are being multiplied together. I would say two terms is more complicated than one term, even though on the left-hand side I have two trigs, and on the right-hand side I have two trigs. The addition or subtraction is more complicated than multiplication or division would be. Is everybody okay with the reasoning there? Okay. So if I look at this, to turn tangent plus cotangent into secant times cosecant, I'm somehow going to have to add these things together, right? Combine them into one thing. So if I look at my identity sheet and I look at tangent and cotangent, I see that using Q1, I can turn those into fractions in terms of cosecants and secants. I like that because my answer, what I'm heading towards, needs to be in terms of cosecants and secants. Can you guys see that? So that would be my first step, is that I would use, Q1 and Q2 to turn tangent into secant over cosecant and cotangent into cosecant over secant. And just as a word on style here, typically when I'm working on the simplifying problems, I'm going to write my work from left to right. When I'm doing a proof of the identity problem, I'm going to work like vertically, up to down, because the right-hand side of my equation is just kind of staying the same in this case. So I'm always going to just kind of write down, and maybe I'll draw an arrow and like with a description of what I did to go to the next step or whatever, but the flow of my work is going to be vertical on these problems as opposed to horizontal on the previous kinds. Everybody, so far so good. So I have two fractions that I need to add together into one thing. To add fractions, I have to have common denominator. What would the common denominator be between secant over cosecant plus cosecant over secant? If I had 2 over 3 plus 3 over 2, what would the common denominator be? 6. How'd you get 6? 3 times 2, right? They're distinct primes. So we'll do the same thing to make a common denominator for secant over cosecant plus cosecant over secant. The common denominator there would be cosecant times secant. Everybody's okay with that? So the first fraction, I need to multiply the top and bottom by secant over secant. And the second fraction by cosecant over cosecant. Everybody feel okay so far? Okay, so when I multiply the numerators out, I'm going to get secant times secant, so that's secant squared, and cosecant times cosecant, that's cosecant squared, and then my denominator is just going to be secant times cosecant. And what are we seeing from here? Who likes the way this is heading? If you look at your identity sheet, is there anything clear to use? Remember, we're trying to get to secant times cosecant. Now, I see that on the denominator, but that doesn't really seem like it's going to be helping me a whole lot here. I mean, I'm asking you guys what you think. Okay. So, yeah, if you look at the Pythagoreans, that's a likely place to look, right? But I don't have sine squared plus cosine squared to use P1. I have a cosecant squared, so I could replace it with 1 plus cotangent squared. But that doesn't really help. Doesn't seem like that's going to help anything, right? It's not going to cancel anything out. If I used P3, well, I have secant squared. I could replace the secant squared with 1 plus tangent squared. But that doesn't really feel like it cancels anything out. So I've gotten to this point and I don't like where this is heading. You know what I'm going to do? I'm going to scrap it and do something different at the start. I'm just going to go back to the beginning and go, this is getting worse rather than better. And I don't see an obvious place to go. So I am going to just, and instead of using Q1 and Q2 to turn them into secants and cosecants, I'm going to turn them into sines and cosines. And try going this way and seeing if this becomes more effective for me. Don't be afraid to do this kind of thing. If you start in on one of these problems and you go a little way in and you're like, I don't see a way to the finish. Seems like this is just going to continue to get worse, or I'm going to be running around like chasing my own tail to some extent. Let's not do that, right? Just try doing something else. So instead of turning them into secant over cosecant and then cosecant over secant, I just went sine over cosine and cosine over sine. Still going to make a common denominator. Still going to do that the same way, multiplying so that I get a common denominator of cosecant times, cosine times sine. Oy, oy, oy. Except I did it to the wrong things, didn't I? You Dumbo. Look what I did. That's supposed to be a sine. Mr. Kulik, starting to doubt you know what you're doing here. Look, it's a Monday. Everybody makes mistakes. Fire drill, or the tornado drill, really got me concerned. Thought I saw a woman riding her bicycle earlier, and I got a little upset. That's a Wizard of Oz joke. One person smiling, I appreciate that. All right, it is you. So if we go ahead and multiply our numerators out, I have sine squared plus cosine squared over sine x times cosine x, and already I like what's happening here a lot better, right? So just did a little simplify there. What do you notice in the numerator? Sine squared plus cosine squared. Yeah, that's just P1, right? What's sine squared plus cosine squared equal? 1. And then I'm just going to think about that as like, instead of 1 over sine times cosine, I'll just think about it as 1 over sine times 1 over cosine, right? We've used that trick before. And that's great because now I can apply R4 and 5. And I have the desired result, right? Because I had way up at the beginning, I had this. It's been on that right-hand side the whole time that I haven't bothered to write down. Now that I've completed my proof, I draw my little square, filled in square at the end to signify to the reader that, like, that's the end of my proof. So, lessons from this. The strategies are just that, they're strategies, right? Sometimes if things aren't working out, the best thing to do is just scrap it and go back to the starting and be like, I had a choice between doing this or this at the beginning. Maybe just go back to the beginning and try doing the other thing if you don't like the way things are heading, right? Did I do that on purpose? Yeah, I kind of did. Because oftentimes I'll see like students get themselves, make a bad choice early on and just like feel like they just need to keep chasing that bad choice when it's might have been more productive to just be like, let's try something else. Try anything else. You know, if you don't like where things are heading, if you're confident you haven't made like a silly mistake, like an algebra error or something, like reduce fractions in a way that they can't reduce, or, you know, forget to make a common denominator, add fractions, or, you know, you do something silly like that, well, but if you think you've done everything right and you're just like, this isn't getting better, in fact, it's kind of getting worse, or I'm getting to a place where I have no clue what to do next, usually that shouldn't be the case. Usually it should be, you get like a couple steps in and you can start to see the finish line up ahead. If you still can't see the finish line after a couple of steps, maybe it's worth going back to the beginning and saying, let's try something else. All right. Should we do another? Yeah, we'll do another. All right, so if I look at this one, the first thing I want to do is look for the simpler side, right? Does one side stick out as simpler than the other? Or the more complicated side, does one side stick out as more complicated than the other? Not really, right? They're both just a single fraction. I would say technically this side is probably more complicated than the other side, because at least with the other side you could split it into like two fractions with a common denominator. So I'm going to start on the left side. Is it always going to be the left side, Mr. Kulik? No, but probably. Okay, so we're going to start here with the left-hand side. What am I going to do as my first step? So there's not an obvious identity staring us at the face, right? Let's look at where we're trying to get to. If I look at the denominator of where I'm trying to get to, what needs to be in the denominator? Cosine. Cosine. Guess what I'm going to do as my first step? I'm just going to multiply the top and bottom by cosine and force a cosine into that denominator because I know I have to get one there at some point. Everybody's okay with that? So often not a bad strategy to look at where we're trying to get to and just like make it happen, Captain, you know? So just like we multiplied by 1 there. So if I simplify things, the numerator is going to be cosine squared. And the denominator, I don't really ever multiply a denominator out when I multiply fractions, unless I have like a good reason to do it. So I'm just going to leave that denominator in a factored form. Because I know to get where I'm trying to go, that 1 minus sign is going to have to cancel out sometime along the way, right? All right. So if I look now, what is the only thing that I would consider? It's really just the cosine squared that I would consider messing with, right? Because I know that 1 minus sine squared just is going to have to get canceled out, so I don't probably want to mess with that. The cosine in the denominator is supposed to be there. I don't want to cancel that out. I want to do something to this cosine squared. Because it has the squared attached to it. Guess where I'm going to be looking? The Pythagoreans. What is the other way I can write cosine squared? 1 minus sine squared, right? That's what I'm going to do. I'm going to use that alternate version of P1 that we wrote to change that cosine into 1 minus sine squared. Because it's like, Mr. Kulik, it's literally the only thing that I could do there, right? I mean, I could do something insane like write cosine squared as 1 over secant squared, but why would I do that? I'm not supposed to have any secants in my answer. At least this has the sign in it because I know the 1 minus sign I have to cancel at some point here soon, right? So if I see this and this and this, What do you notice about those three things? The 1 minus sine squared, the 1 minus sine, and the 1 plus sine. That, to me, looks a lot like this difference of two squares factoring pattern, right? Guess what I'm going to do with that 1 minus sine squared? I'm going to factor it. So 1 minus sine squared is a difference of two squares, so it'll just factor to 1 minus sine, and then 1 plus sine. And now we see some nice stuff is going to happen, right? We can reduce the 1 minus sines. And we're now at the finish. You guys kind of see what we saw there? So in general, when I see like a 1 plus sine or a 1 minus sine or a 1 plus cosine, a 1 minus cosine, something like that, I'm going to be thinking I probably want at some point need to factor or multiply by the conjugate or something like that, because it's almost always going to be a trick that I'm going to have to pull out on when I see that in the problem. Right, at the beginning I saw I had 1 minus sine and a 1 plus sine. At some point I figure I'm going to have to factor, turn a cosine squared into 1 minus sine squared and factor to reduce. Alternatively, at the beginning, we could have multiplied by 1 plus sine over 1 plus sine. That would have been okay. Like, hey, let's just get the numerator there. Could have done it that way as well. It's really just going to be kind of the same steps afterwards. Has the advantage of, instead of factoring, you just have to FOIL and then use P1 and reduce. But either is okay. All right, I'm going to do one more, and then we're going to move on to that note sheet that I passed out to you guys at the beginning, and I'm going to take some random, we'll call them volunteers. You don't really have a choice, though, to help us work our way through those. And then after that, we'll release you guys to kind of work on some homeworks. Oh, I lied. I have two more. I have this one and another one after that. All right, if I look at this one, what's the more complicated side, left or right? Left. No one would argue with that, right? The left-hand side has clearly got a lot more going on than the right-hand side. All right. What do you think we should do as a first step here? Well, if I look at the numerator, what do I see? That's that difference of two squares factoring pattern, right? Do I have any 1 plus cosines or 1 minus cosines in where I'm heading? In what I'm trying to get to? No, man. Well, let's FOIL that out then, because I know that it's going to leave me with a Pythagorean afterwards. And maybe that'll be helpful. And again, I'll write FOIL, but I'm just using that difference of two squares factoring pattern that was in the strategies at the beginning to just jump straight through the foiling. If you wanted to foil it, though, that's fine. You'll get to the same spot. It's okay to do that. So far, so good? What do you think you want to... Oh, well, question here. Can I just do this? No, why not? Because of the minus. Yeah, it's an addition or subtraction problem. Got to be careful when we reduce those guys. It's either the whole addition or subtraction problem or none of it. You can't just reduce a part of an addition and subtraction problem. So what should we do then if I can't do that? Yeah, let's do P1, right? 1 minus cosine squared is? Sine squared. Yeah. Ooh. Ooh. Where am I trying to get to again? Tangent squared. What do I have? Sine squared over cosine squared. That looks familiar, doesn't it? What is that? That's Q1, yeah. Sine squared over cosine squared is just tangent squared. And I'm done. That wasn't so bad. Even though that left-hand side looked kind of scary at the start. What do you guys think? It's okay? Again, once you get more comfortable with building some intuition up of, like, ooh, I see something that looks like this, that's usually a clue to, like, what to do to start. All right. These get easier as they go. In a way, I like these better than the simplifying ones because I have an answer, right? I know where I'm trying to get to. If things are going badly for me, it's like I can see it going badly because it's like I feel like I'm getting further away from where I'm trying to get to. Allows me to abandon that method and try something else in a way that, like, with the simplifying, I don't really, not really sure, other than, like, Mr. Kulik says it's going to be like one thing. Okay. All right, let's take a look here. So if I look at this, which side do you think you want to work on? The right does look like the more complicated side, correct? When I look at this piece, though, somehow that's going to have to turn into a sine squared and a cosine to the fourth, right? Can you kind of see that? So the only way that's going to happen is having to factor some stuff, right? I don't love that option. Sure. Alternatively, this sine squared and the cosine to the fourth would have to turn into that stuff if I worked on the left-hand side. That looks more like a FOIL problem. I think I'd rather pick foiling over factoring if I looked at this. So I'm going to, again, break the general strategy and pick what I think looks like the easier side, or looks like the less complicated side. But Dykes, because of looking at this, it seems like I'd rather foil than factor. So I'm going to take the side where I can get away with foiling instead of factoring. Again, the more complicated side is just a general suggestion. You can violate it. In fact, all these problems are doable regardless of which side you start with. They're all doable. Sometimes they're easier than others, but it's okay. All right. So the first thing that I'm going to do is look at what I'm trying to get to. So I need to have a cosine all by its lonesome. So the first thing that I'm going to do is I'm going to rewrite cosine to the fifth as cosine to the fourth times cosine. Because that cosine at the end, I'm not touching that guy for the rest of the time. That part of my answer is set. Does everybody feel okay? Makes sense as to why I did that? Now if I look at what I have here, this has to come from the rest of this, right? Now, the right-hand side has only signs in that other parenthesis. So the sine squared, I don't want to touch either, right? Because I can just multiply that sine squared in and hopefully it'll take care of itself. It's the cosine to the fourth that I want to worry about messing with. Does that feel okay? So I don't have an identity for a cosine to the fourth, but what I do have an identity for are cosine squareds, right? So what I'll do here is, again, I'm just going to rewrite cosine to the fourth now as cosine squared times cosine squared. Does that feel okay, what I did there? Now, the reason I wanted to do that is because I have a way to take cosine squared and write it in terms of sines. What identity will help me do that? P1, right? P1 will allow me to write cosine squared as 1 minus sine squared. So again, all of this stuff now needs to turn into that, right? But I like the way things are looking because now everything has a sign in it at least, right? So what do you think I should do first? I'd FOIL, right? I have the 1 minus sine squared and 1 minus sine squared sitting right next to each other. Let's FOIL that out. That feels like a pretty obvious thing to do. So 1 times 1 is 1. 1 times negative sine squared is negative sine squared. Negative sine squared times 1 is negative sine squared. Negative sine squared times negative sine squared is positive sine to the fourth. And then these two guys I could combine, right? So just do some combining of like terms there. But I like where this is heading because I got that trinomial piece that I'm supposed to have. The only problem is that the exponents are wrong, right? Well, that's okay because what do I still need to do? If I go back and I look at my final answer, there's nothing out front of that trinomial piece, right? So, seems to me we should just distribute that sine squared through, right? So 1 times sine squared is sine squared. Sine squared times negative 2 sine squared is negative 2 sine to the fourth. And sine squared times sine to the fourth is sine to the sixth. Remember, we're adding exponents when we multiply, right? And what do we notice now? That's actually exactly what we're supposed to have. And we're done. Whoa. Oh no. Okay. All right. So let's have you guys take a look at your notes sheet. And I'm going to do some random volunteering. You guys will help me just by kind of answering my questions. Okay. Edie, so you're the first one up. So if I look at this very first problem, notice there's no sines or cosines in it, right? So this very first problem is going to be done with all just algebra techniques. There's no identity that we could use on this because there's no sine, cosine, secant, cosine, whatever, right? So trig in it. What do you think the very first strategy we want to employ here is?
Common denominators?
Yeah, so clearly we're going to be working on the left side, and I would make a common denominator as the first step. So what would that common denominator be?
X minus 1 times x plus 1.
Good. So the first fraction will multiply by x plus 1 over x plus 1. So when we do that, we'll have x plus 1 times x squared minus 1, and then x minus 1 times x squared minus 1. It's probably okay, but I'm going to tell you right now, there's an easier way to hit this. Edie, do you see the easier way we could hit this?
Oh, is it to factor by
Yeah. Yeah, what if we factored the numerators to start? Great job. Now, you would get to the finish line doing what we did. And it's not wrong to do what you did. You could FOIL that stuff up and combine like terms, and it'll be kind of yucky. The factoring after you do the combining won't be easy, or won't be as easy as what it was here. But if instead we factor x squared minus 1, just factors x minus 1 times x plus 1. And then what do we notice?
You can cross out the
Now, this is going to be the most common mistake students will make is what I wrote here. What I've written is wrong. Let's see who my random person I'm going to ask what I did wrong was. Grace. So what I've written there is wrong. What mistake did I make? I made it on purpose, because I would guess that 75% of us would write exactly what I've written here if they tried to do the same thing themselves. Do you see what it is? Okay. It has to do with the subtraction symbol.
They don't cancel out.
They, what's they? I'm not sure what you mean by they.
Like the x minus 1, the x plus 1.
So that part is correct. The canceling is correct. What I've done to go right from there to there, though, is incorrect.
I don't know. It's like, I don't know.
Okay, let me ask you one more question, and then I'll leave it, okay? If you look at the left-hand piece that I have here, this right here, what do you notice that, what symbol is in that piece that I didn't copy on the next part when I copied to here? What did I leave off?
The like fraction.
Okay, what else did I leave off, though? You're right, but that's not what I was looking for.
Parentheses.
Mm-hmm. Now, if I write this, this is okay.
Yeah.
Now, do I need that first set of parentheses? X plus 1 with the parenthesis around it?
Yeah. No.
No, because there's nothing in front of it, right?
Yeah.
And I can't combine the stuff inside it, so I can just drop those. The second set of parentheses, though, do I have to have those? Yes. What is it? What is that second set of parentheses telling me I need to do? I have to distribute that negative through the entire set of parentheses. Would Mr. Kulik be so mean as to reuse that same trick again? Oh yeah, that's a good one, guys. That's a good trick.
So that's the final answer.
Yeah, because it said we're just trying to get equal to 2, right? So we'd be done at that point, right? No identities on here because there's no trig things in it, right? It was just all going to be an algebra thing. Yes, sure. We're going to skip the second problem because we already did it. That was the first example problem we did. So we'll just skip that. We already did it. All right. Emmy, looking at the third one, what do we notice here? Which side would you want to start on, left or right? I agree. What strategy are we going to employ here? So there's not an identity typically to start, right? If I look at, I don't have like sine squared plus cosine squared anywhere to use, or any sine squareds or any cosine squareds to use P1. But look at what we have on that left-hand side. So you should notice that we have 2 fractions that we're being asked to add. So what would we want to do first? That's what we should do first. What would the common denominator be? Okay, so if I just had 1 over 3 plus 1 over 2, what would the common denominator be? How'd you get the 6? That's correct. Multiply the 2 denominators together, right? Guess what we're going to do here? The common denominator is going to be secant x minus 1 times secant x plus 1. Just multiplying the 2 denominators together. Does that feel okay? Okay. So if we simplify things, secant x plus 1 times 1 is just secant x plus 1. Secant x minus 1 times 1 is just secant x minus 1. And my denominator is secant x plus 1 times secant x minus 1. Everybody okay with how I simplified things down?
But the bottom's not the same thing.
The bottom and the top are different. The bottom is, or the top is being added, and the bottom is being multiplied. Right? You see the difference there?
Yeah.
Okay. Page. What do you think next? Okay, are you looking at your identity sheet?
Yeah.
Because it's not going to be helpful yet.
Okay.
So look for an algebra things. What do you see in the top of our fraction here? Yeah, we can combine some like terms, right? When I do that to the top, what happened? What do I get when I combine like terms in the numerator? Well, they're not being multiplied. If I have x plus x, what do I get?
2.
Okay, if I have secant plus secant, what am I going to get?
2.
There you go. And what about the 1 and the negative 1? They 1 plus negative 1 is 1?
No, 0.
Okay. Yeah, so those just kind of cancel each other out. Look at where we're trying to get to now. Guess what we just found? We found the 2. Fantastic. I love that, right? That's great news. What do we have going on in the denominator? Page? Yeah, but more specifically, you have like an a plus b times an a minus b. Is that a good sign or a bad sign? That's a great sign. We love to see that because we know how it foils out, right? That's our difference of two squares where we just get a squared minus b squared. All right, Paige, I've tortured you enough. Thank you. Josh, you're next. You should, yes. Are you looking for something in the numerator or denominator? Yes, agreed. We just got done foiling that difference of two squares out. What kind of identity do we often follow that with? Yes, which one? For secant?
P2.
For secant?
P3.
P3. So secant squared minus 1, if you look at P3 and we subtract 1 from both sides, secant squared minus 1 is equal to tangent squared. Okay, that's good. And let me give you a hint now. Is everybody ready for the hint? So I'm going to go back and I'm going to look at where I'm trying to get to here. When I go here, it looks like I have 3 things multiplied together, right? So I'm going to rewrite this as 3 things multiplied together. One of them is obviously going to be the 2, right? We pointed that out already. Now, if I look at the denominator, that's tangent squared. Do I have a denominator in the origin or in the where I'm trying to get to? Is there a denominator in where I'm trying to get to?
No.
No. So that tangent squared in the denominator can't stay there. Do I see part of where that denominator of tangent squared is going to go when I look at the goal? What do you see?
And the denominator.
What is cotangent the same as? 1 over tangent, right?
Oh, it's the same as the denominator.
Yeah, so well, it's not the same because I have a tangent squared. But I know that, like, I'm going to take part of that tangent squared and kind of stuff it or break it off by itself. And just do some clever rearranging here. So I'm breaking it into 3 things. I know the first thing has to be a 2. I know the second thing has to be a 1 over tangent. And everything else I'm going to stick into the last part, because hopefully that's all going to cancel out and give me cosecant.
So that's the 1, 2, 3.
Yeah. So like I have, this is this part, like this is going to be this part,
Oh,
and then like this is going to be that part. That's my hope. So again, I looked at what I was trying to get to here because we've done some stuff and we got it down into one thing, which I'm happy about. There's no more addition and subtraction. Somehow this is going to have to break apart and give me that. I'm just kind of looking at it and going, okay, I got just multiplication division going on now, so I can kind of break that apart any kind of way I like. Let me see, how do I want to break that to chunk it up? Does that feel okay, everybody? All right. Matt Vogel. What do you want to do next here? Yeah, so that's R6, right? And then I would suggest here also doing R5 and Q1. Nope, let's not do it that way. Let's not do R5. Let's just do the secant over cosecant version of Q1. Everybody's okay there? Now, let's look at this thing and think about this for a minute. So I'm probably going to think about it really as the numerator is secant over 1. Because we got one of these weird complex fraction things, right? Everybody feels okay with me thinking about it this way? What can I reduce now? What's the same in the fraction on top as the fraction on bottom? The numerators, right? The secant is in the numerator of both of them. They're identical. They can just reduce out. So what I'm left with then is like 1 over cosecant. When I look at this, this is the reciprocal of the reciprocal of cosecant. If I do the reciprocal of a reciprocal, what's that's the same as? right? Let's say we start with 2. What's the reciprocal of 2? 1 over 2. What's the reciprocal of 1 over 2? 2. So I have, what's the reciprocal of cosecant? Cosecant, right? And what's the reciprocal of the reciprocal? Cosecant, right? So this is just going to be like doing nothing at all. And guess what? That is exactly where we needed to land, right? Now I kind of like did an aside there to talk about like how that canceling was happening, because my suspicion was if I just crossed off the secants and then wrote cosecant there, everybody was going to think, was going to be doing it for the wrong reasons. Been like, oh, okay, that's the only thing left. It's like, whoa, 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 what about all the 1 overs that are left there? I want to make sure that we're clear as to like how that reducing really happened. Do you guys feel okay on that? Okay. All right. And then we did this one already. We did that in the notes, right? Already. So let's move on to this is our last one. All right, Mariana. Which one do you want, or which side do you want to start with? You want to do the left side? Okie dokie. So again, I see 2 things being divided, 2 things being multiplied. I don't see much difference between the 2. That works just fine for me. So if we work on the left-hand side, keep in mind where we're trying to get to. I see that I have a cotangent squared in the numerator, and I'm supposed to have a times cotangent in the denominator. So I'm going to take one of those cotangent squares from the numerator. And just like move it out front. And then that guy I'm not going to touch. Everybody feel okay with that? That's always a nice first thing to kind of look for. So somehow cotangent over 1 plus cosecant, so those are all supposed to be used, has to turn into secant u minus tangent u. Mar, are you okay? What do you think we want to do here to try to get cotangent u over 1 plus cosecant u heading in that direction? What should we do first? So if you want to rewrite everything in terms of sines and cosines, I think that's a reasonable idea. So you could use like Q2 and like R5 or whatever. I think that's reasonable. I don't know that there's another one that I would try to do there. Oops. It's R4. Well, that's where we just were, right? So you could, it's not wrong to do that. If this is the route that we go, I would probably at this step clear the fractions. So I would multiply like the top by like sine u over 1 and the bottom by sine u over 1. So what that'll allow us to do is kind of get rid of the fractions inside of the fraction. So we're left with just cosine u on top. And on bottom, we're left with sine u plus 1. Well, it would if it was cosine over sine, but it's sine plus 1. When I see something like that, though, sine u plus 1, what should I be thinking? The strategy that I would employ is that difference of two squares strategy. So what is the other half that I need? Yes. So let's multiply the top and bottom by that. So whenever I see like a plus 1 and a minus, or like a something to the first plus 1 or something to the first minus 1, almost always it's going to be helpful to do a multiply by the conjugate type of thing. That's typically not going to get you in any kind of trouble. So I do that. On top, I'm going to have cosine u times sine u minus 1. And on the bottom, I'm going to have sine squared u minus 1. So if you wanted to factor that denominator and reduce, you're just going to end up right back there where we started. The key is that piece in blue, sine squared minus 1. That I can use an identity on. Close. So I know 1 minus sine squared is cosine squared. But here I have sine squared minus 1. What do you notice is different about the signs? The SIGN S's. Well, they're flipped, right? Here, on the top one, the sine squared is negative. On the bottom, the sine squared is positive. On the top, the 1 is positive. On the bottom, the 1 is negative. You see that? So what is the bottom one going to equal? What's the cosine squared on top? Is it positive or negative? Positive. What are all the signs on top compared to the signs on bottom? They're flipped, right? So the bottom should equal negative cosine squared. Right? If I think about it as this instead, positive, negative, negative, positive. Positive should be negative. You see that? The alternative would have been, instead of multiplying by 1 or sine minus 1, you could have done 1 minus sine. There, and then everything would have worked out nicely. Because sine plus 1 and 1 plus sine is the same thing. That's okay. All right, so we have cotangent u over cosine u times sine u minus 1 over negative cosine squared. Now, something really great has happened. Do you see it? Look at the fraction. You notice that the denominator is just cosine squared. The numerator has a times cosine in it. Let's reduce that. Is that okay? You would have saw it. In fact, you probably did see it. You're smiling like, oh, you have a lot of faith in me, Mr. Kulik. I do. Now let's take a moment and go back and look at what we're trying to get to. We have the cotangent already out front. We need secant minus tangent, right? So here, that's two things. Right now we have a fraction, that's one thing, right? So what you should do is, since that denominator is one term, I'm going to rewrite that one fraction as the difference of two fractions with a common denominator. Everybody's okay with that? What's sine over cosine? What's sine over negative cosine then? Negative tangent. What's 1 over cosine? Secant. What's negative or 1 over negative cosine? Negative secant. And there I have minus a negative, right? So minus a negative we know is a positive. And that's what we're trying to get to, right? It's secant minus tangent, but negative tangent plus secant is the same thing, right? Okay. For next time, what I'd like you guys to work through is 47 to 54. Yeah. 47 to 54. That's like 8 of those guys. They're not all as hard as the ones we did today, but they're going to be challenging to start. Like it's one of those things. You just need to spend some time, like hunker in. Like it takes some time. There's no like magic pill, like you just do it the same way every single time. It's like it is for a solving problem. It's one of these that just takes some experience to build up some intuition. The better you are acquainted with the identities, the easier it is to kind of see your path to the finish. Some of us can probably getting to the point where after a step or two, we can kind of see the way to the finish. Be like, okay, I see where this is heading. I think I can finish this guy out. That's where we should be heading at this step of the game. a lot of these we should be seeing where that finish line is before Mr. Kulik announces and we're done, right? We'll see you guys on Wednesday.